Welcome back, students, for our penultimate lecture. In the last two lectures here in Chem 502, we're going to discuss computational chemistry. So we're going to go into a little bit more detail about how we can run computer programs to simulate problems of interest for us in terms of chemical reactions and so forth. And so in this lecture, we're going to start by reviewing computational chemistry and going over some of the basics of computational chemistry. And then in the next lecture, we're going to look at models that move beyond the Hartree-Fock model that we talked about before. So a month or so ago, we discussed the Hartree-Fock model as a way to approximate the energy of many electron atoms. Recall that in this model, we treat electrons as if they exist over a region of space determined by one electron orbitals and reduce the effective nuclear charge felt by the electron being considered. The process is then repeated for all electrons, so we determine where every electron in the molecule is, and then we iterate this process over and over again until we reach an energy minimum. This technique was the first attempt to get good energy levels for many electron atoms and molecules in terms of computational chemistry. In the decades following, researchers have improved quantum mechanical calculations, both in terms of the mathematical models used and also the basis sets used in the model. Recall from talking about the variation theorem a month or so ago that the better the guess is, the better the answer you can get. In these last two lectures of the semester, we're going to look over these models and see how quantum mechanics can be used to solve modern chemical problems. So the learning goals for today are going to be to determine some of the things that we can answer using quantum mechanical calculations, some of the ways in which we can use them to aid our research. We're going to review the Hartree-Fock model, and then we're going to apply the Hartree-Fock model to some situations and see what it's good for. One of the best things about computational chemistry is that it can allow us to view what happens in a chemical reaction. If you think about it, going between reactants and products in a reaction necessarily involves an unstable transition state that can't be observed experimentally. When we use computation, we're able to simulate both the reactants and the products, and we can even simulate the transitions between them if we so desire. A simple example that we can do is shown here, involving the torsion angle of butane. We learned in organic chemistry that the anti-conformation is the most stable, where the methyl groups are opposed to each other. And we also have gauche forms that are somewhat stable, but less stable as the methyl groups are near each other. And then any overlapping form is highest in energy, as can be seen up here. Of course, these high energy forms are not actually observable in experiment. And all we can see is what is actually occurring. Maybe we can sample some of these low energy states. Using computational chemistry, we can actually simulate the butane at any bond angle we want. So we can simulate the energy of the anti-conformation, the gauche conformations, and even these high energy conformations to show that in fact the anti-conformation is lowest in energy, and these gauche conformations are also reasonably low in terms of energy. If we wanted to, we can even do complex geometry optimization calculations where the computer will simulate a lot of different conformations until it stumbles upon an energy minimum. And at this energy minimum, it assumes that that is the lowest energy conformation that can be adapted, and it gives you that conformation as an output. We can use this for more complicated processes as well. So here we have a simple question of what's the ideal bond torsion angle for butane, but we can also look at this in terms of chemical reactions. So all chemical reactions can be modeled as one of these reaction coordinates where we have reactants at high energy and products at low energy. This seems to tell us that we would go towards products. The products are at a lower state of energy. We would tend to form those spontaneously. However, reaction is opposed by the transition state. So the transition state here is always higher in energy. And again, these high energy conformations are not observable. We can observe reactants, we can observe products, and we can kind of think about how we get from reactants to products, but we can't actually see that because these molecules don't really ever exist. But we can simulate them computationally, whether we're talking about bond torsion angles or any other type of process. So I've done some, I don't do too much computational work, but I've done some simulating of water. And you can simulate water with different bond angles and show that indeed the best bond angle is 104.5, just like we would expect. But computation allows us to simulate linear water and 90-degree water, whatever sort of water we want. And we can do this and figure out what the energy are. We could also do things like simulate 5 bonds to carbon, like you might expect in a transition state. If you're adding one molecule, maybe leaving a chlorine or something, a good leaving group there. And we can simulate these things. Before I move on, there's a couple of interesting things that we can talk about based on this reaction coordinate. One thing we can note is that the products are at lower energy than the reactants, like we already talked about, and therefore we would expect the reaction to proceed in the forward direction spontaneously. This is a question of thermodynamics. Another thing we can observe is that this activation barrier is relatively high, and so it might be hard for molecules to actually react. And this is a question of kinetics. We're going to look over both thermodynamics and kinetics in a lot of detail next semester. So that's what we're going to be going on once we come back from Christmas break. With this in mind about how we can use quantum mechanical calculations, let us revisit the Hartree-Fock model, and we'll start by considering what energies we need to describe the helium atom. The helium atom has 2 electrons, and we need to describe the kinetic energy of both of these electrons. These electrons also have Coulombic attraction to the nuclei, and they have Coulombic repulsion amongst each other. If we wanted to move on and look at molecules, so not atoms, but molecules, we would also need to consider nuclear repulsion, that these molecules are actually repelling each other. And they are also moving as well, they're vibrating and so forth. So what we can do is come up with some Hamiltonian. Here we have the kinetic energy of the electrons. Here we have the attractive energy with the electrons to the nucleus, and then we have the repulsive energy of the electrons. This is for an atom. And if we were talking about molecules, we have those other terms in as well. Now, I don't include those other terms that are necessary for molecules because this equation is hard enough and is already unsolvable. There's a problem that we have here in that this is not spherically symmetric. So the electrons, we have this 3-body problem. The electrons repel each other in a way that we can't really describe. And so we can't analytically solve this set of differential equations. There is no one solution for this. So does that mean we're out of luck and we can't solve it? Well, no, it doesn't. We talked about this in class earlier when we first brought this up, is that we also can't solve the differential equations for sending a rocket ship to the moon, and yet we do that. So how do we actually go about doing this? We need to use an iterative approach that takes a trial wave function as an approximation for the actual solution, and the better our guess, the better the solution. We'll start by going over the basics of the Hartree-Fock model that we've already used in class. The Hartree-Fock model gets around the problem that we can't solve because of the electron correlation by ignoring the electron correlation. So the Hartree-Fock model, like we mentioned before, treats electrons as diffuse charges unless they're the one of interest. And what these diffuse charges do is reduce the effective nuclear charge that our one electron we're considering feels at any given point. This boils the problem down to a spherically symmetric one, and we can actually get solutions. Now, this one allows us to solve the Schrodinger equation, but it double counts electron repulsion, which gives us systematically 2 positive energies. This is something we'll see as we go through looking at some of the predictions that quantum mechanical calculations make, is that we often get systematic errors where we get the same error because of our assumptions that we put in. And if we know that, it'll help us kind of compare to experiments and so forth. So how do we actually use the Hartree-Fock model to solve for energy? All we have here is a way to make up wave functions that might solve the Schrodinger equation. What we do is we use the variational method. We come up with a trial wave function and we use the symbol capital Phi here. We try to pick as close as we possibly can to the actual wave function. And in our wave function, our trial wave function, we have parameters that can be varied. And these parameters are optimized to give the optimal energy. Now, we'll talk more about these next time, but the way these look is essentially we have sets of function that describe the different orbitals. And what we do is change how much of each of these sets of functions we add in. So how much S, how much P, and so forth. And that's mostly the way in which these things are working. We have our variational theorem that tells us that the energy of the trial wave function is equal to this integral here. This is the same thing we've been doing before. So we take our wave function, we operate it on it with our operator of interest, and multiply it by the complex conjugate of our wave function, otherwise known as the expectation value. And then if it's not normalized already, we normalize it down here. The variational theorem tells us that this is always greater than or equal to our actual energy. So if we happen to guess a wave function that's actually in a solution, which is impossible for many electron atoms, we would get the exact energy. Otherwise, we're going to be off slightly. Another thing that comes out of this is that the better the guess, the better the trial function, the better the results. And we can use many different trial functions, and these trial functions are called basis sets. And we'll look more into different basis sets. Last time, we've already talked about these, and mainly the basis sets that are used are Gaussian functions. They're not necessarily the best solutions, the best fit for the orbitals, but they are easiest for computers to integrate and so forth. So they're what gets used, hence the name Gaussian. How does the Hartree-Fock model hold up? It turns out that it really depends on the problem at hand. Their main downside is ignoring the electron correlation. So if the problem that you're addressing isn't affected by electron correlation, the Hartree-Fock model is actually adequate despite its gross simplifications. Certain properties such as equilibrium geometry or dipole moments are relatively unaffected by electron correlation. So let's look at a couple examples here. First, we'll look at relative energies of structural isomers, and we see that we have pretty good comparisons to experiment. So what we have here in this experiment column is experimental data. In this column over here is computational data, and then this delta column is the differences. And so you can see they're actually, pretty close. In the case of acetonitrile and methyl isocyanide, it's spot on. And in some other cases, we get, various differences, but they're reasonably close. Now, why is this so good? Well, in these isomers, the electron correlation is pretty similar in both cases. So ignoring electron correlation for acetonitrile gives you the same effect as ignoring it for methyl isocyanide. So the actual prediction is pretty good, close to the experimental value. Another thing that's even better is comparisons for a proton affinity, so the strength of bases for various nitrogen bases. This is another example where here all we're doing is adding a proton to a molecule or even changing the electrons much less. We're not changing the structure at all. And we see pretty close agreements, a little bit better than our other structural isomers. Other things that we can use are calculating optimal geometries. Again, the electron correlation is not super relevant here. And so we can see pretty close predictions based on our experimental data. Now, note here something that we can see. So our numbers are very close. So looking at ethane, we get a Hartree-Fock bond length of 1.527, where an experimental bond length predicts as 1.531. So if you were to get something like that, that close to experimental data, you would be thrilled. And so that's pretty good, and that's rightfully so. Our bond lengths here that were predicted with our simple model is really good. Note, however, that every single prediction is shorter than the experimental value. This is an example of the systematic error that's introduced. So something that's based on the assumptions that we're putting in here is giving us smaller bonds than we actually observe. We're mainly ignoring the electron correlation, And so something about that is we double count this electron correlation, we're giving us double repulsion and so forth, and that is affecting our experiment. We're predicting smaller bond lengths. We can see another thing that these are similarly good in terms of predicting the dipole moment. Again, we see this systemic error of being a little bit greater than we would normally predict. Are there any problems that this doesn't work for? Yes, of course there are. And here's a couple of examples on the next slide. So one big failure of the Hartree-Fock model is in terms of homolytic bond association. So cleaving a bond and leaving two radicals as a result. In this case, we're going from fully filled orbitals to half-filled orbitals. That's going to make a huge difference in electron correlation if we have paired or unpaired electrons. And so we see really way off predictions, way low that rather than we expect. So they're much lower than we see experimentally. Another thing that they're not super good at doing is figuring out stretching frequencies. So I've done some of this in our class that get the frequencies, but we can see that they're off by a fair amount. Again, systematically increasing the frequency, predicting much higher than it actually would be. So with this, we can see that the Hartree-Fock model is useful and can be useful in some situations. Next time, we're going to look at ways that we can improve the Hartree-Fock model to be useful in more situations. In general, what we're going to see, and we'll look through some examples of this, is that there is a trade-off between computing time and accuracy that underlies every computational experiment. So when you undergo to do a calculation, you have to think of how accurate do I need to be, and then how much time do I have? Because there's a big difference between calculations that take 10 seconds and then those that take 10 days to do. And you can imagine doing some calculations like this. I was in grad school, I did some not quantum mechanical calculations, but I did some simulations involving protein folding, and those would take 2 days on a good day to run. And so I was limited in the numbers that I could do. So you want to make models that allow you to maximize your efficiency and also answer the questions that you're going to address. And we're going to be thinking about that a little bit next time as well.